You can come over here. There are seats here. Arnab, आगे आ जाओ. This is mine. So, I think we'll start. Welcome you all for this much-awaited Nobel Prize Colloquium. As you know, it has been the practice that we have 3 talks on Nobel Prize on physics and physiology and medicine, physics and chemistry every year. And this year is no exception. As you know, in the first week of October, we have the Nobel Prizes announced. On 6th October, the Nobel Prize for Physiology and Medicine was announced for the groundbreaking discovery of peripheral immune tolerance, which prevents our own immune system from harming the body. Professor Sulabha Pathak here will talk about it today. And Sulabha, thank you for coming and agreeing to give this talk. Thank you very much. The very next day, Physics Prize was announced, and that was for demonstrating quantum mechanical effects on macroscopic setting, namely quantum tunneling effect and energy quantization on an electric circuit. Professor Vijayaraghavan from DCMPS will talk about it. It turns out that Vijay was associated with all 3 Nobel laureates. Michel Devore was his PhD supervisor, and he has papers with the other 2. So I didn't have to try hard to find the speaker for Physics Prize. Finally, the Chemistry Prize, which is a story full of holes, but which will enormously absorb your attention. I lifted this from the Nobel announcement. And Professor Jyotishman Dasgupta will talk about it. So this is for the discovery of metal organic frameworks, which has room for putting molecules in, and can do a variety of things. So you'll hear about details from this. So we'll have these 3 talks. Each talk will be of 20 minutes duration. And we will have 5 minutes after each talk for questions, immediate or urgent questions. But we will also have, I've reserved 15-20 minutes towards the end, after all 3 talks, for more open, free-flowing discussion. So with this, let me invite Professor Sulabha Pathak to start off this to talk about the prize on physiology and medicine. Sulabha.
So let me start. Am I audible? Great. So let me start with first thanking the organizers for giving me this opportunity or a reason to visit TIFR once again. I have retired in 2019. So, and of course, all of you for actually coming and hearing us speak. So I have labeled this as Nobel Peacekeepers because tolerance is about keeping peace. And actually, Sakaguchi, when actually had attended his talk when I was at MIT, and he had called it Peacekeeper cells, and that kind of stuck in my mind. Because the audience is full of many students, let me also explain that this is a laser pointer? Yeah. This particular thing should have a citation, because it's not my work. But after the Nobel Prize was announced, I was idly looking at some things, and I found this attractive cartoon, which I modified slightly, and I just kept it for fun, not realizing that I could use it for this talk, which also means I therefore do not have the citation for it. So it is my error, which I'm admitting, and I hope the students don't do such things. Next time you like some cartoon, please take down the citation. With that, let us start with So Nobel Prize for Physiology and Medicine for this year was awarded to Sakaguchi, Brunkow, and Ramsdell for the discoveries concerning peripheral immune tolerance. for this to understand their work then, we must first understand what is immune tolerance and then go ahead towards the peripheral immune tolerance. So as you know, since there are many physics and chemists as here as well, let me remind you that the immune system is an intricate system of organs and cells that is protecting the body from thousands of different microbes. But at the same time, it is supposed to cause minimal collateral damage to the body. Thus, the basic idea behind how it's going to work is its discriminatory power, the old problem of us versus them, as President Bush very nicely put it. So the immune system must recognize and spare or tolerate cells and selectively recognize and attack the non-self cells. So how does, okay, now this guy has started already. How do I stop it? We'll do it again. So this discriminatory power then is on two levels. The first level, which is rather crude, I would say, is our rapid acting forces of the body, the cells, the innate system, which is our rapid acting force. It is non-specific to any particular pathogen. That means it will as well attack Staphylococcus aureus or Streptococcus or E. coli, whatever it deems as not good for the system, non-self. And this is a very crude level because it is only recognizing certain molecular patterns on the surface of those cells. It's as simple as, wearing a red. Okay, everybody having a red t-shirt is out, or everybody having a green t-shirt is going to be a threat. Or if you're in the current dispensation in many countries, Western countries in the world, if you have a pigmented skin, you are going to be a threat. So that is how that works. And how do I go and get this going again?
Go back.
Go back. Okay, yeah. Yeah, maybe that will help. Yeah. So what you're seeing here is a neutrophil, is a white blood cell, which is actually pursuing these diplococci or streptococci that are running around. You see, it is neglecting all the RBCs that are around and only wanting to attack or remove that particular cell. This is, like I said, only because of the receptors that those cells are expressing, the molecules on the surface of the cell. And just to interesting sidebar, this was taken by David Rogers on a 16 camera in 1950. And it has been around since then. And I think it beautifully shows you what the discriminatory power at the first level is. The second level is the adaptive immune system, which is slow to develop, but is very specific. It is specific for a particular pathogen. It also looks as if it has memory. What do I mean by it has memory? Well, the first innate immune system did not have memory. What is memory? A recall mechanism, right? So the adaptive immune cells seem to have a memory because every second time or third time you encounter the same pathogen, the reaction is faster, better, as if the body remembered. The cells remembered who it had seen for the first time. And this is important in vaccinations, of course. That's why we have to take a minimum of 2 vaccines to remind the body. You had seen this before. Okay, so this is because the cells of the adaptive immune system have receptors that recognize pathogen-specific molecules when expressed on cells. And here I have to go somewhere to, oh yeah, great. Okay. So here what you are seeing was a large self cell, that is the cell of the body, but which was infected with the flu virus. And this was a lymphocyte which was directly targeting and killing that self cell. So this is why I'm saying this specific. If this macrophage, this cell, was actually infected with some other virus, say HIV, this particular cell would have let it be. It would have gone away because it does not recognize the molecules that are being expressed because of HIV. And therefore we say that it is specific. So then these this discriminatory power of the adaptive immune system is the one that we want to concentrate on because it is also directed against self cells. And two types of cells are involved in this adaptive immune response. The B cells and the T cells. These are called B cells simply because in mammals, they mature in the bone marrow. T cells because they mature in an organ called the thymus that exists in the body. So B cells are the ones that produce antibodies. And this is well known for everybody. So every time we talk about antibodies, that these are very specific molecules that are being produced by them. So they are rather uninteresting. The really interesting guys are the T cells, who are the central players of the immune system. They come in two varieties. The first is, again, these two varieties are based on the molecules that are expressed on their cell surface. The first is the CD8 positive T cells. So these cells express the molecule CD8 on their cell surface. And the video that we saw earlier, killing the large cell was this CD8 positive T cells, which is a cytotoxic. It actually is a killer cell. The more interesting one are the CD4 plus T cells. That is cells that express the molecule CD4 on their cell surface. And these are the conductors of the orchestra of the adaptive immune system. They are the ones who wake up the immune system and push it into functioning. So then the question for many years was, how is the body populated by T cells and B cells? But I'm going to just talk about T cells, the more interesting cells here, but this applies equally to B cells, expressing receptors that recognize molecules that are not expressed by cell cells or expressed by cell cells, both ways, right? So where does the discriminatory power come from? So during the development, the progenitor cells that go to the thymus in the case of T cells or the bone marrow in the case of B cells, during the process of development, they acquire receptors that are capable of recognizing a wide variety of molecular conformation. This is a completely random process, which means these different T cell is going to have a receptor which is going to recognize something else. And because it's random, it also means that it's going to recognize molecules that are expressed on your own cells as well. So self-receptors are also being formed in the thymus, T cells in the thymus. And then, however, during maturations, cells expressing self-reactive receptors are eliminated, are killed. So a large number of T cells are being formed, a large number of T cells are being pushed out. And only those which do not recognize self cells are being pushed in the body. And this is called the concept, the central tolerance, because it is dictated by single organ in your body. And Burnett and Medawer in 1960 got their Nobel Prize for the discovery of this central tolerance. So 65 years ago. However, even during that time, it was known that self-reacting cells do escape to the periphery, are found in your blood. And then the question is, how are these self-reactive cells kept in control? What is the peripheral mechanism of tolerance that allows and keeps the self-reactive cells in control? Not much was known for a very long time. Obviously, there are other mechanisms are in place. And these could be simple ones like shielding important organs from immune cells, like the brain and the eyes. Immune cells don't go there much. So that even if they have those molecules, they are. But that's not enough to explain. Then there is insufficient stimulation when self molecules are. So if a T cell recognizes a self cell, there is not enough stimulation for it to get activated and become, really work further. Again, this is a good enough idea, but not enough to explain what is really, the kind of control that we see in the periphery. There were some experiments that suggested that certain T cell populations could suppress autoimmunity in both in vitro experiments as in vivo experiments. And this was then a whole new field came up in the 1970s called the T suppressor cells. I remember actually reading and discussing heatedly about T suppressor cells. But these experiments were not definitive. They were really not very clean. And the claims were extremely exaggerated, so that the whole field fell in disrepute. And that is where we were when enter Shimon Sakaguchi. So born in Japan, he did his MD and PhD from the Kyoto University, came, like most of us do, go to a different country to get some postdoctoral experience, expand your perspective. In this case, he went to the US. He was deeply interested in autoimmunity. So he returned back to Japan as an investigator for Riken. Eventually, he went to various institutes, including Kyoto Medical Sciences, Kyoto University. And finally, he moved to Osaka, where he still works when he was awarded the Nobel Prize. So Sakaguchi was extremely interested in autoimmunity, and whatever the field said, whatever the skepticism, he was convinced that there were suppressors, or what he would like to call peacekeeper cells, in the periphery. The experiment that set him on this path was a very simple one. So when newborn mice, 3-day-old mice, the thymus is removed. The education that the T cells get to remove all self cells does not happen. And so they escape to the periphery. Such mice then grow very sick and die because of extreme immune activation against their own cells. However, when mature T cells from a healthy donor are transferred to the mice, they remained healthy. What does that tell? Sakaguchi was convinced, therefore, that something somewhere in these T cells were populations of cells that were calming the immune system down. So he first established that the cells that were doing this job were of the CD4 variety. They were expressing CD4 T cells. And then it took him almost a decade to show, in 1995, he finally demonstrated that these T cells, which calm the immune system, also express a molecule called CD25 on the cell surface. And so, very simple experiment, simple now. I'm sure it takes years to get these things done. But so what he did was, you take T cells, remove CD4, you take, first of all, for all CD4 plus T cells, remove CD4 plus, CD25 plus C cells from the population, and then inject them in those thymectomized mice like before. If you remove this fraction, the animals got sick, were not healthy. You add that fraction, and the animals were healthy. So therefore, he could prove that there were indeed CD4 positive, CD25 positive T cells that were acting like the peacekeepers of the immune system, and he called them regulatory T cells. However, the problem with this is that CD25 is also expressed on many T cells that are activated. So the field, and of course, with the experience of T suppressor cells, the field was really still skeptical about his findings. Enter Mary Brunkow and Fred Ramsdell. Mary Brunkow was born in the USA, did a PhD at Princeton, and then joined Darwin Molecular, which is an industrial research place in the USA. This was then acquired by Chiroscience and eventually Celtech. And it is here in Celtech that, along with Fred Ramsdell, she performed the Nobel Prize-winning work. In 2004, when the lab closed down, she moved to systems biology, and it is there that she now continues to work. Fred Ramsdell, also born in the US, got his PhD from UCLA, and joined, after a fellowship, joined a pharmaceutical company, and eventually joined Darwin Molecular, which became Celtech, and worked with Brunkow on this project. So now, of course, later, after 2004, when Celtic closed down the labs, he went into a number of other places and finally to Sonoma Biotherapeutics, which he has co-founded, and he continues to work there. So what did they do? Now, both in Darwin, one of the areas that Darwin molecules or Celtic was interested in was autoimmunity. So they decided to work with the scurfy mouse. So what is this scurfy mouse? It is actually an product of the Manhattan Project, where scientists were exposing animals to radiation and studying the effects. In this one, there was this fluke mouse called scurfy mouse because the male mice had scaly and flaky skin. Scaly and flaky meaning scurfy. And these male mice were short-lived and suffered from severe autoimmune disease. The liver, the spleen were heavily enlarged and they died young. The female mice, however, remained unaffected, which meant whatever the mutation that had arisen because of exposure to radiation had come was on the X chromosome. So they decided to identify this scurfy mutation. This was the early 2000s. Today, DNA and gene technology has gone so far that what they took 10 years to do, we could do in 5 or 6 months, even lesser perhaps. So the DNA, the X chromosome of mice has 170 million base pairs. It was literally trying to find a needle in the haystack. They narrowed it down to about 500,000 base pair, which is about 20 potential genes that is right in the center of the X chromosome. Then they set out methodically to test each gene and trying to see wherein lies the mutation. As luck would have it, out of all the 20 genes that they tested, they found the mutation in the last gene that they tested, the 20th gene. And trying to tell again, the students don't give up, sometimes it is the 20th gene that matters. They found that there was a 2 base pair insertion in this one, which meant that the transcription factor that was required, or whatever the protein that was formed, was truncated and therefore ineffective, not being able to function. So, and because this area had a homology with the forked box genes, they named this FOXP3 for forked box P3 gene. And they then also, of course, proof of the pudding, right? You knock it out, you get something, you knock it in, that should go away, simple. That's exactly what they did. They proved that the wild type FOXP3 gene rescued the scurfy mouse from disease. Now started, it's all very well to say this happens in mice, but mice are quite different from humans. We have to prove that it happens in humans too. So what they had begun to suspect that there was one particular disease called IPEX. That was a fatal autoimmunity found only in boys, and the boys died young. So they started suspecting that the scurfy mutation equivalent could be IPEX. Their hunch was correct, but it was not easy because this is a rare disease. So they had to collaborate with a lot of pediatricians to get samples from all over the world. And they eventually proved that the IPEX defect, that is a defect that causes autoimmunity in boys, was also because of the FOXP3 gene. Thus, they convincingly established that FOXP3, the transcription factor, is involved in controlling autoimmunity in both mice and men. Of course, Shimon Sakaguchi was looking at all this very interestingly. So immediately he jumped on that as well. And he then demonstrated that the FOXP3 was selectively expressed on his T regulatory cells. So they were becoming regulatory because they were overexpressing FOXP3. And in fact, if you want to identify T regulatory cells now, we regularly do staining for FOXP3. And of course, the retroviral transfer of FOXP3 genes into conventional T cells who are not T regulatory cells became T regulatory if they had added FOXP3. Ramsdell, meanwhile, was also busy with work, and he showed that Tregs were absent in the scurfy mice and overexpressing FOXP3 in these mice increase the number of T cells. So, of course, this is much later, genome-wide analysis of this FOXP3 target genes. They found that 700 genes and miRNAs are actually involved in T cell receptor signaling, cell communication, and transcription regulation are involved. And FOXP3 is that has the potential to act on these many things in the. So the critical finding of this year's Nobel laureates is that in both mice and men, autoimmunity is caused by the breakdown of peripheral tolerance because of the absence of one cell type, the T regulatory cells, and this one cell type is because of one gene locus, FOXP3. Okay, so then just a couple of minutes for what do T regulatory cells do. So if they are balanced, you're healthy. Of course, when the number reduces, you have autoimmunity, and the reverse is cancer. So just quickly running through this. So they are, of course, important in maintaining self-tolerance and preventing autoimmunity. They are also important in avoiding fetal rejection because remember, in the growing fetus, a completely foreign body in the mother's womb, and it is not rejected because of this. It is important in controlling chronic inflammation that happens. And it also regulates immune responses to infectious diseases. Many infectious diseases, including malaria, you die not because of the parasite, or you have problems not because of the parasite, because the strong immune response to the parasite, which also is happening in COVID-19, right? So Tregs will be important in controlling that. And of course, during transplantation, if you do not want transplant rejection, Tregs will be involved in that as well. The flip side is if you have a dysfunctional Treg component, you have a number of autoimmune diseases. Tregs support that is the most really one that in cancer, normally you have about 5 to 10% T regulatory cells in the peripheral blood. During cancer, this can go up to 50%. And in the especially tumor microenvironment, it's quite often populated by T regulatory cells, which is also an evasive mechanism to escape immunity. Then, of course, I mean, parasites and microbes are not going to be behind. It's a very common immunoevasion strategy for many pathogens to activate T regulatory cells. It is also now very clear that it is implicated in type 2 diabetes, obesity, atherosclerosis, and some neurodegenerative diseases. So if you have obesity problem, you can sometimes say, oh, it's my Tregs, what can I do about it? So these are the far-reaching consequences of this work. And the groundbreaking discoveries of Sakaguchi, Brunkow, and Ramsdell helped us explain one of the major conundrums of immunology. The first was answered in 1960. Now the Nobel Prize winners in 2025, 65 years later, are telling us about what can be done for peripheral immune tolerance and to multiple ways to alleviate human suffering. Just as a matter of interest, as of March 2025, 260 clinical trials are trying to leverage T regulatory cells. And when this Nobel Prize was announced, just out of curiosity, I looked up T regulatory cells or Tregs in the title. 13,000 papers are talking about that. And I have not even added FOXP3 in the title, just to let you know how far-reaching are the consequences of this year's discovery. And with that, I stop. I hope I was exactly in time. I checked it.
We can take 2 or 3 quick questions, Ravi.
So what is the function of FOXP3?
It's a transcription factor. So it controls or switches on or switches off multiple genes or in the T cell regulatory, T cell signaling, etc. So what happens is then if you don't have FOXP3, you do not have these switched on to convert them to T regulatory cells, because once you become T regulatory, you have your pattern, you express molecules, you function differently than when you're not T regulatory cells. I can tell you more about that if you're interested.
Yeah, go ahead.
So
Is the developmental trajectory of T-Rex cells
Sorry, I can't hear you.
is the developmental trajectory of T-Rex cells known very well? As in, are they?
They're formed in the T-Rex are two types. They can be formed, they are formed basically in the thymus during maturation, but they can be induced in the periphery as well.
Is there one more question?
Great talk. I had
Thank
just
you.
one question. So you mentioned that the initial experiment by Sakaguchi was that they removed the thymus from 3-day-old mice.
Yeah.
But the maturation of T cells, which also involves the selection between CD4 versus CD8, because initially all like the preliminary T cells have both CD4 and CD8.
Correct.
If that happens in the thymus, then how does that bifurcation happen in thymusless mice?
Okay,
Cool.
so I think what you're trying to ask me is, so the age of the mice matters because most of this weeding out and development does happen in the early neonatal stages. When T cells are developing, they develop both CD4, CD8 positive, and then the thymic epithelial cells give them signal to decide to push them into this or that. Does that answer your question?
Yeah, but if there's a lack of a thymus, then how do these T cells become active enough to have an overactive immune?
So see, the T cells are, because the thymus was there up to 3 days, right? The T cells are present and there's no regulatory component. Tregs are less now and therefore they're being activated because many T cells are actually were formed, but there was not enough control in the periphery because there were not enough Tregs in the periphery.
As compared to nude mice, which
Yeah.
don't have a thymus.
Yeah.
Thank you.
So last question here, Ravi.
So clinically, the only definitive diagnostic criterion for autoimmune diseases is like anti-nuclear antibodies and anti-centromere antibodies, right?
No, not true at all. It all depends upon what you're looking for. For example, for rheumatoid arthritis, you would be looking for IgM antibodies that are against synovial tissues. So different, lupus, it's different. What you're talking about is lupus, but so depending upon what autoimmunity is, what is autoimmunity, whatever.
Everything you mentioned is antibodies. Those are produced by B cells.
Correct, but
So this means the
okay.
classification.
No, hold on.
Entirely different.
So B cells produce the antibodies, but B cells require T cell help to become active to produce the antibodies. So if the T cells are controlling what happens, activation of B cells don't get activated, you don't get autoimmune responses. But we
Is the
also
help
have
coming from Treg.
Yeah. Okay. Yeah. Sure.
So we will
We'll
have
discuss
20
it.
minutes towards the end.
Yeah. Oh,
So we'll move on to our we'll move on to our next speaker. Let's thank Sulabha again.
ये sort of laser pointer use करना है.
Yeah, can I? So we'll next Vijay will tell us about physics Nobel Prize. Vijay.
All right. Thank you, Manoj, for inviting me. In fact, if you remember, you were speculating that there is ChatGPT told you that Nobel Prize is going to go to quantum. And I said, no, it's not possible. And then I think after half an hour after the announcement, I messaged Manoj saying that I will give the talk. Sorry. Okay, so that's the citation for the discovery of macroscopic quantum mechanical tunneling and energy quantization in electric circuit. As Manoj said, I was privileged to have worked with all three of them in various capacities. Of course, Michel was my PhD advisor. I was his first PhD student in the US after he moved from France to Yale University. And I'll say more about John and both the Johns later on in the talk. So we need to introduce a few basic concepts since it's a wide variety of audience here. So very quick introduction to the essential quantum physics we need to understand the subject of this prize. From high school days, we learn about the atomic model in this simple picture like a solar system. Later on, those who continue with physics learn that this is not really accurate. Erwin Schrödinger talked about that you cannot basically describe electrons moving around in these fixed orbitals. You have this idea of a wave function, which only gives you probability distribution. So these images here are electrons around a particular atom in different energy states. And the shape of these pictures here gives you the probability distribution of where you can find the electron. And of course, Schrödinger won the Nobel Prize for for these developments. And if I now improve this picture and make these orbitals kind of fuzzy, it's still not very accurate, but to say that we don't really know where the electron is, and that's really how nature seems to work. The first set of observations, you can now say that, well, this idea existed even in the simple picture. There are these different circles, these are the orbits of the electrons, and you can label them, and these correspond to different energy, right? So one thing which immediately strikes you is that you cannot have other energies which are in between. Only certain energies are allowed for the electron when it's around a nucleus. So you have this first new idea that you have these quantized energy levels. This was already known, and Schrodinger's equation sort of proved that from first principles. And the second new idea, which came about from the development of quantum mechanics, is that if you now label these electrons in these different orbitals as some kind of a state, which are described by these wave functions, it turns out that the equations of quantum mechanics allows you to create states of these types. I can put the system in a state which is like a combination of A and B, or A, B, and C, or even a combination of A minus B. It sounds bizarre, but this is what nature works, and we call these quantum superposition states, right? So you had this one new idea of having only energy levels which are discrete and quantized, and then you had this idea that superpositions exist. The Nobel work is actually not connected to this concept, but then there is one other associated concept, which is the quantum tunneling. And I'm sure many of you have heard about this, but very generically, here's a simplistic picture. When we think about some kind of a particle which is approaching a barrier, a wall or something, in our regular world, which is the classical world, this ball will always bounce back. It'll hit, it'll stop there, or it'll bounce back on the other side. Now, when you express the same situation in the quantum equations in the quantum world, so we are now imagining an electron approaching some kind of a barrier, then because the electron is described in terms of a wave function, which tells you that it's sort of spread out in space, you don't really know where it is, it's somewhere there, the equation actually allows that the wave function can leak through this barrier and have a finite value on the other side. And because these are sort of probability distributions, it means that there is a finite chance that the system will reappear on the other side. This is a very simple picture of what quantum tunneling is. It comes from the fact that objects and particles are described by this wave function, and in the quantum world, with the right kind of barrier, you can have a finite probability for this wave function to exist on the other side, which in the classical world, we would call as the forbidden region. Okay, so what are the examples of this kind of quantum tunneling? Things like radioactive decay. When a nuclei escapes when it's strongly bonded with the full system, it has to go through a tunneling process to escape. Nuclear fusion happens like that. When two nuclei collide, they actually are undergoing a tunneling process, and then suddenly they become one. More things which we are familiar about, scanning tunneling microscope, which brings a tip very, very close to the surface, and electrons can actually hop across that gap, even though there is no conductor there. And this is quantum mechanical tunneling, and it's used to map surfaces. And you also have something called a tunnel junction, which is just a sandwich of two metal surfaces with a very, very thin gap, or an insulator. And you can have electrons tunneling across a small gap, right? So this device is actually crucial for the experiment. We'll discuss a slightly modified version of this device. Okay. Now, the point is that till now, I've still been talking about atoms and electrons, right? We are somehow okay with the idea that these weird quantum laws are applicable in this regime where I cannot even see what's going on. It's very, very small. I don't care. I don't worry too much about it, right? But what about bigger objects, right? Clearly, we never observe this person appearing on the other side of the wall, right? So this is the human equivalent of the picture I showed you earlier. So this doesn't happen. And in fact, Erwin Schrödinger was very bothered by the extension of quantum ideas and applying it to an object like a human or a cat. The famous Schrödinger's cat experiment, a lot of people misinterpret this. In fact, Schrödinger invoked this to say why this looks so bizarre, that if I extend my ideas, which I'm interpreting from what quantum equations are saying, and I take it to an object like a cat where basically a radioactive atom can decay or not decay, it's probabilistic, and that then triggers a mechanism which would eventually kill the cat. But because you don't know whether the system is going to happen, and if you have enclosed it in a box, you sort of invoke this idea that, well, the cat must be both dead and alive, right? And clearly, we know that that doesn't happen like that, and they would also interpret that nobody did this experiment. So the question really was, this was actually an important question, somewhat philosophical as well, but still an important technical question, like how large can a system be and still show quantum effects like the ones we just discussed, right? So enter the Josephson junction. Here is the same picture I showed you a couple of slides ago, but now instead of two metals, I'm using a special kind of a metal which becomes a superconductor. So these are metals which lose all resistance below a certain temperature, and you have a very thin insulating barrier. This is the only slide with some equations for the experts. Don't worry about it. The next slide will explain this pictorially. Okay. So here's an actual picture of such a Josephson junction made in our lab here in TIFR. What you're seeing is a metal film here and another metal film which is underneath, and there is a little overlap region. So this is not made sort of horizontal like in the picture, but one on top of the other, and there is a very thin layer of insulator, in this case aluminum oxide, and the metal is aluminum, and that's actually how you make these Josephson tunnel junctions. So Brian Josephson, one other thing. So this kind of a structure is characterized by two quantities. There's something called I naught, which is the critical current, and then there is a capacitance, right? Why is there capacitance? Because it's basically a capacitor. There are two metal plates separated by a dielectric, an insulator. That's what a parallel plate capacitor looks like. And this critical current comes from the Josephson relations, and there is this quantity called the phase across the junction. I will come to that in just a second. And Brian Josephson basically studied this system and showed that as long as the current flowing through this device is smaller than a critical value, it still does not, first of all, it allows current to flow through, which means that the charge carriers are tunneling across this barrier here. But there is this relationship between the current and this quantity called the phase. And there is a second Josephson relationship which relates that the voltage developed across this circuit element, so you can imagine measuring the voltage across this, is related to the rate of change of this quantity called the phase. Okay, which means that if the phase is constant, which will happen for a constant current less than I naught, delta does not change, and hence the voltage is zero. So this composite object consisting of two superconductors separated by an insulator effectively behaves like a superconducting wire, which does not dissipate any energy because no voltage is appearing across it, right? Now, in fact, we define this phase in the modern understanding by inverting this relationship. So we actually define that this phase is actually the time integral of the voltage across this device. It is also interpreted as the phase difference between the quantum wave function describing the superconductor on this side versus that side. These are all equivalent definitions depending on what you're trying to do. And if you're an electrical engineer and you understand inductors and capacitors, you can just think of this as a flux. That's what it is. It's renormalized flux. There is a constant here which sort of makes it dimensionless. But that's what this quantity is, okay? An additional property is that now this device called the Josephson junction is labeled by the symbol cross. That's the symbol for the junction. And you also add this capacitance, which is always going to be present, right? And if you play around with these equations, you see that this Josephson junction actually looks like an inductor. So you have an inductor and a capacitor, and that forms an LC oscillator. And the reason this is important is that this means that this system actually has a natural frequency, which is given by this inductance, which is connected to the critical current, and the capacitance. And all of these properties are set by the dimension of this particular device. Okay. So Brian Josephson analyzed this and won the Nobel Prize in 1973 for this. Okay, so now the pictorial representation. So here is the device, your Josephson junction and the capacitor, and it's connected to a current source. And I've put some resistor here to sort of represent that whenever you interact with your environment, there is always some amount of dissipation. And dissipation in electrical circuits is represented by a resistor. And this system can be understood by looking at this kind of a potential well and where the particle is sitting at the bottom. The natural frequency I talked about in the previous is the natural frequency of oscillations if I disturb this system at the bottom of the well. So if I tickle it, it'll oscillate back and forth. Okay. So this is the steady state system when there is no current flowing through this device. The Josephson phase, which is sort of plotted on this axis, is a collective degree of freedom involving a vast number of pairs of electrons or Cooper pairs, because we are talking about a superconductor. So that is the macroscopic thing here. We are not going all the way from a single electron to a cat, but we are going from a single electron to a system which is composed of a vast number of electrons or Cooper pairs acting together. A simple way of understanding this collective degree of freedom is to look at a pendulum. In fact, the equations of motions of this system is exactly identical to that of a mechanical pendulum, where the phase can be replaced by the angle theta, right? So imagine that if I wanted to describe the motion of this pendulum, how we do it in high school is by just using this coordinate theta, because that is all I need to know where the pendulum is. If I can define the theta, I can define it. But I can imagine a more complicated way of giving the positions and momentum of every atom which is making up this pendulum bob and the wire, but that is not necessary, because in this case, the relevant degree of freedom is this collective degree of freedom, which is the angle. So this is the analog of what is happening here, that the Josephson phase is a macroscopic collective degree of freedom composed of many, many microscopic gradients, but that is the relevant quantity which we are interested in. And this is the quantity the 3 Nobel laureates identified to play around with. Okay. Just a side note for the experts, the superconducting state itself is often considered as a macroscopic phase, because it is a manifestation of a large number of Cooper pairs all in the same ground state, which is often referred as the Bose-Einstein condensate as well. And the Cooper pairs are also tunneling as the current is flowing. They are tunneling across the junction. And this is not the tunneling we are talking about, because that's just the electrons tunneling. This is the microscopic form of tunneling. There is going to be another tunneling which is going to come up in the next few slides. Okay. So now the actual experiment. So just stare at this figure for a reason. So there is the same thing, the current you can pass through this junction. X-axis is voltage, y-axis is current. And what this graph tells you is that if you increase the current, you remain at 0 voltage, this black curve here, and then at some finite current, when you exceed the critical current, it jumps into a finite voltage value. And then you have this linear IV curve, which is basically the IV curve of a resistor. So this is what happens. And then when you reduce the current, it undergoes some weird mechanism and comes back to the 0 state, and it shows a symmetric behavior on the negative side. So this gives you 2 different states. When the current is less than the critical current, the voltage is 0, and that's the superconducting state or the 0 voltage state. And when the current is greater than the critical current, the voltage is finite, and that is called the normal state or the finite voltage stage. As you change the current, that potential I showed you, it changes like this. It basically tilts. In American parlance, this is often referred to as the tilted washboard potential. Washboard, because apparently, I don't know, they used to use this washboard to wash clothes, which has this undulating potential, and this kind of looks like that, right? So physically, what you're imagining is that once you exceed the critical current, this barrier, which is sort of trapping the particle here, slowly disappears. And then that phase particle runs down the hill, and that is basically the voltage state. So when the system is trapped here, that's the superconducting state. And when the system gets untrapped, which naturally will happen when you tilt it far enough meaning current greater than the critical current, then it just runs down. And this now gives you the signature of measuring this transition from the 0 voltage state to finite. All you have to do is measure a voltage. If you are 0 volts, it's superconducting. If it is a finite number, it has changed into this region. Okay. So all of this is now the basic experiment they did. But why is this relevant here? Okay, so here's the same picture again. Now imagine a scenario where you're very close to the critical current, you have not exceeded it. The potential looks like this. There is a very small bump here, which you have to overcome in order to escape. So in reality, you don't have to exceed the critical current for this jump to happen, because there is always noise And in the ideal case, this noise is just coming from the finite temperature at which it's operating. So this phase particle is sort of jiggling around here, and there is a random chance that it will go over this barrier. And once it goes over the barrier, it is not able to stop, even though the barrier has not dissipated, because it sort of gains enough momentum that it just runs down the hill, and the transition from the 0 voltage to the finite voltage state happens right there. Okay. Now imagine that I'm in this scenario and I keep reducing the temperature. So I keep suppressing the ability of this particle to fluctuate and hence escape out of this. Chemists should recognize this as the Arrhenius rate law. This kind of activation process happens all across chemical reactions. But once you go to sufficiently low temperature, quantum mechanics tells you that there is a new way the system can escape. It doesn't have to go over the barrier. It can tunnel through the barrier. And this is what is called macroscopic quantum tunneling, if they could observe. Now, the question is, how do I distinguish whether this is happening or this is happening, right? In the output, when you look at the voltage, there is no way to know whether the escape happened via tunneling or via over the barrier. You cannot tell that. So they had to look into the physics of this exact system and figured out what signature to look for to demonstrate that it is actually quantum tunneling. So just to summarize, there are two ways it can escape: activation over the barrier or tunneling through the barrier. So I'm not going into the details of the experiment, but the crux is you can measure how fast the system is jumping out of this metapotential. Like, you keep doing the experiment over and over again. And from that, you can figure out an effective noise intensity. How much noise is there which is causing the system to escape? If there's too much noise, it'll escape very quickly. If it's too little noise, it'll escape very slowly. And you can turn that into a temperature. Okay, that is the temperature which is plotted on the y-axis, which is called T escape, the escape temperature, or the temperature interpreted from the escape rates. And the x-axis is the physical temperature at which this circuit is operating. So you do this in cryogenic systems like dilution refrigerators, so that you can control the temperature from, say, a few hundred millikelvin down to something like a few millikelvin. This data here is actually data taken by myself and my postdoc when I was at Yale. And you see that here at high temperature, the escape temperature follows the bath temperature. And then it sort of stops there. That's the smallest temperature we could do the experiment till. The dashed line shown there is basically showing where we stopped. But the prediction, if this was to be limited by quantum tunneling, is actually the lower line. Okay, I'll come back to this point. Here is the data from the Nobel Prize winning experiment, where if you look at the black dots, for which correspond to this thing called the quantum junction, I will explain that in just a second. You see it follows and then it stops there. And the arrow here actually marks from the theory, which is actually the summary of that theory is given here, is that if you are at low enough temperature, this effective escape rate saturates at a value, which can be turned into a temperature. And that temperature has this value here, and that is marked here. And they see that their junction exactly at that temperature stops to, become basically escaping slower and slower and saturates here. This was the proof that this has to be due to tunneling, because if it was due to activation, that rate would have kept going smaller and smaller. Now, if you showed this data for the first time to anybody, they will immediately say, okay, but how do you know it is saturating because of quantum tunneling? If you did not do your experiment carefully, there could be excess noise in your experiment. And this was the biggest challenge of this experiment. This was also the biggest challenge I faced when I did this experiment myself in the early 2000s, that to show that your system is actually not limited by your bad experimental design or unwanted noise in the system. So what they did is, because this value of the temperature depends on that frequency, which I mentioned, it's related to that small oscillation frequency. This frequency is connected to the critical current. They could apply a magnetic field in the same experiment and reduce the critical current down to this value. So they show that when they made the thing smaller, this number went lower, and their junction actually followed that to a lower temperature. So this showed that the earlier saturation could not have been due to noise, because otherwise this would have also saturated at the same level. So this was the big thing here. right? So, and then the last thing was related to it's connected to this experiment, the evidence of energy quantization. What it tells you is that this system which is sitting, we are imagining this as a pendulum, it actually cannot have arbitrary energy. It can only have certain amounts of energy, and you can calculate this using quantum physics equations and the shape of this potential, which is precisely defined by the current and the properties. And what they showed is that at specific frequencies as calculated, the extra energy you are giving causes the system to jump up and then increases the probability of switching out. That's what these peaks are. They're showing that at specific frequencies and specific currents, you get these enhancements, and they could connect it to the calculation which showed that this can only happen if the energy was quantized. Otherwise, you would have only seen one special frequency, right? So this was really the big deal. Now, these kind of experiments we do routinely in our lab in a much more simpler and easier way, and that's basically what this whole field led to. You can take these circuit elements and you can custom design your Hamiltonian, your potential energy shapes. And the reason this award has been given now is that this was the stepping stone of the whole field of superconducting quantum bits, or often called artificial atoms. Each of the three Nobel laureates pursued one particular design. Michel Devereux pursued Cooper pair box and contronium, which was also connected to my thesis work. John Clark focused on the flux qubit, and John Martinez focused on the phase qubit. This phase qubit is the closest design to the experiment I described here. All of these just vary in the values of the capacitor, Josephson junction, and the inductor. So you have this playground to completely change what you want, and you basically have a toolkit to build custom quantum systems. So that's really the reason why, and this field has now become very, very big. So superconducting oscillators as quantum bits, tunable properties, you can do high fidelity control, very good measurement, everything is driven with simple microwaves. You can control the environment and engineer the baths, you can make customized Hamiltonians and do all kinds of wonderful things. So that's essentially the reason why they won this award. I'll just end this talk with just a couple of slides of my own experience since I worked with Michel. I was trying to dig up pictures. So this is an old picture from a beach party in 2004. That's a young-looking Michel. He was probably close to 50 at that time. And one particular memory in terms of, I was lucky because I was his first student. His family had not arrived. We would spend hours, like 4 or 5 hour discussions every day in the lab. And that was an enormously helpful experience for a young graduate student. Much of my other students who have gone and worked with him have not seen him for more than 2 or 3 times in the entire year, right? And just one anecdote here I remember is that he was very, very insistent on making good presentations, and everything had a meaning, right? So when I first went with my first presentation to him, I made a list of points which looked like this. So he stared at it for a minute, and then he asked me, Vijay, what is the algorithm behind your color scheme? It took me a minute or two to even understand what he was asking. I was like, what color? I mumbled, oh, it looks good. So he was very peculiar. Every color had a meaning. Blue was ground state. Red was excited state. Purple was the color of new. Brown is something, we don't understand. There are all these different ideas which he had to do. But this was actually a fantastic experience in that Yale group where all the other research groups also played a huge effort. We used to spend hours discussing our presentations, but I usually would get comments like this. There was one practice talk where after the whole thing ended, everybody tore my talk apart. I was literally in my tears, and all Michel had to say, I think your font size is still too small. But it was an incredible experience. He's a great scientist. I finally graduated. Here are some pictures from my graduation. Michel, of course, came to TIFR as well. And for some strange reason, we don't have any pictures of him in TIFR. But there are other pictures. We were at Gateway of India in Bangalore. There was a small group at that time. We had gone to a conference. This is somewhere in Bandra. This is on top of the director's flat. At that time, the director's flat was not being used by Mustansir. So it used to be given as guest house. So we were able to get him to stay there, and the terrace access was given at that time over there. So that's basically it. Thank you.
Thanks, Vijay. A few quick questions. Ravi again.
Thanks, Vijay. Fantastic, actually. So, what are the parameters that describe that energy landscape that you showed, actually, for the Jyotishman engine?
So the question is, which parameters define the energy landscape? It directly connects to the critical current of the junction and the capacitance and the amount of current you're flowing through that. So the equations I shown earlier, you can just take the quantum version, you can exactly calculate those things. Like, yeah.
But there's ruggedness you can apply.
So, we have one more talk to go, so. No current can go.
Yeah, food will not be served.
Hello. Sir, what was the physics behind macroscopic tunneling? Why it was happening?
No, so it was not that why it was happening. People wanted to know, can it happen? Can a collective degree of freedom, like if I want to say the angle of the pendulum, can it tunnel through a barrier? That's what the experiment showed. And the modern understanding is that if you're able to isolate that degree of freedom sufficiently from the environment, then you can do it. The big technical achievement of the experiment was to choose the right system and be able to engineer it in such a way that all the bad things which happen to quantum systems can be controlled. And the general idea is that by the time you are at the level of a cat, much before, it is impossible technically to isolate that system from the environment. So you just cannot describe the system using the simple equations, and hence you don't see any of these effects. So
But
that was the reason.
Here tunneling is happening, right?
Yes.
Then why it's happening? Why?
Because it can.
Yeah, I think we should move on to the next
Yeah.
speaker. Thank you, Vijay,
Yeah.
again. We will have time for questions.
Oh,
We will have
forgot.
time for, we'll come back.
This is one such device which we bought from our lab, so you can pass it around just to see.
So we will have 15-20 minutes in the end. So our next speaker is Jyotishman Gupta. He'll talk about the chemistry Nobel. Jyotishman.
Okay, thank you, Manoj. Of course, it's Manoj, this is a dream for all colloquium coordinators. You have everybody in the house. So it's really a pleasure to talk about a chemistry Nobel Prize, which is actually for chemistry. This is actually for the development of metal organic frameworks. And one of the critical aspect of these development of the framework, you will, by end of the talk, realize that technologies can be built on these frameworks, and really technologies which would be useful for all of us. So the architects of building these metal organic frameworks are these three gentlemen: Shushumi Kitagawa from Kyoto University, Richard Robson from University of Melbourne, and Omar Yagi from UC Berkeley. All of them, of course, have shared 1/3 of the prize, but at the end of the talk, you would see why this guy deserves a little bit more attention. He called for it, and he had been predicting it for 3 years that he will win it. But along came these two gentlemen with him. So this is the framework that we are talking about. It's not limited to this design, but you can see the beautiful architectural aesthetic part of it. It's all crystalline. These blue parts are what we call in graph theory like nodes, and this is a linking these nodes. So these are all organic molecules, which Manoj missed while he was talking about the frameworks. He said metal frameworks. So the organic part are the links that hold the metal nodes, and they are all beautifully positioned to give you this 3D architecture, which is reproducible if Manoj makes it, if I make it, if GRK makes it, any physicist, chemist, or biologist makes it, if they know the rules of the game. It's absolutely a chemistry synthesis marvel. The simple idea is, if we know what the node's symmetry looks like, and if we choose the right kind of linkers, I would get exactly the same class of structures, which means this is programmable design, okay? This framework is the actual structure of the framework that should come right at you is actually encoded in the components. the symmetry of the components, the interaction between the components, the way this is to be put together. So that's why for all the physicists in this audience, this is an important number to think about. What is the length scale of order in the system? This is on the order of the macro crystal. So if I can build a millimeter size crystal, the order in the system is in the length scale of that. That means every piece of it, from the nanometric size which you see here, close to a nanometer to 2 nanometers, is repeated over a millimeter length scale. And that's why this deserves the prize. Not just that, for chemists, and this will biologists will touch very closely too, we know that enzymes in biology have cavities that can do reactions. It's called active sites. And those active sites have typically a very specific number of the length scale in which chemistry happens. It's close to a nanometer to 2, less than a nanometer. The enzymes themselves are close to, length scales of 2 nanometers to 3 nanometers, depending on what objects you're talking about. But those have these cavities which are small. But these programmable frameworks, the chemists can only do this, by the way, the most creative parts of the scientific community. They can go up from 0.5 nanometers to 10 nanometers, repeated exactly the way we want, right? So this is a critical feature of this. Now, the way I look at it, and I'm not from the field, but I look at it from a very simple perspective, the civil engineering of skyscrapers. The idea is these skyscrapers never existed when bricks and mortars were used to build houses. When it shifted to iron frame, the grids were made of iron frame. You started building large number of floors on top of each other because the tensile strength and the modulus, Young's modulus, would be sufficiently good enough to keep the weights in balanced out on a frame. Later on, chemistry, of course, you move to an alloy, which is a steel, and it became lighter, and you could build even bigger skyscrapers. This is exactly the iron to steel transition you will see even for the metal organic frameworks. I'll show you today. Okay, so this is the idea. You have a metal node. Now, this is a metal node which is slightly more complicated because it's a metal cluster, and these are linked by these nice linkers which are purely organic, as you can see. This is a benzene group pretty much in between, okay? For those who are sitting outside or maybe far away, this is just a 6-member ring, which is an aromatic backbone, a benzene, right? So now the 3 architects, Omar Yagi actually developed this. This is the Roger Federer of the field. It's the most beautifully made structure that precisely shows the power of the field. This is Richard Robson and Sushumi Kitagawa. I tell you how these two engaged in the initial ideas to lead Omar to ultimately putting this all together. So the big chemistry challenge it has always been, and this existed in pre-1990s, that in chemistry, organic chemists were the top echelon of scientists simply because they could make materials as they wanted. Okay, it's always been that case, but these materials, people knew that they made it based on what intuition they have. They would either look at nature, some pharmaceutical drug can be taken out from leaves. An organic chemist, given the challenge, yeah, I can make that structure as complicated as an isotropic, but they could make it. But those structures are essentially in chemistry called zero-dimensional structures because they're closed structures, right? Now, before 1995, there was a prediction, or there was a statement made by one of Nature editors, very powerful editors, who said that in physical sciences, when we think of making crystalline structures, there does not exist a code to make structure that I want. Organic chemists can make any molecular structure at the 0th level. Looking at the structure, they can make it. But for extended solids and structures which are crystalline, there was no such code. What rolled Hoffman another Nobel Prize, a theoretical a computational person who had a preeminent chemist who talked about orbitals and symmetry. He gave the statement as late as 1993 that organic chemists are masterful at exercising control in 0 dimensions. One subculture of organic chemists have had an exercise of control on the 1 dimension, which is the polymer chemist. And this was this is Hermann Staudinger, who started the entire field of polymer chemistry when they started these 0D objects being connected link by link in a 1-dimensional polymer. And these polymers could, be amorphous because they would start, the persistent length will not be bright enough and they will start collapsing on each other. So these are, of course, pretty important work because from isoprene you can have rubber, and without polymer, you can't function nowadays. This prize in 1953, we still are being a benefit, we are still benefiting from this prize because everything around us is polymer now, but it's 1-dimensional. So what Roald Hoffman said, what happens in 2 dimensions and 3 dimensions? This will be something of a challenge for the chemist. So the question was, don't worry about amorphous stuff. Let's think about crystalline materials. So is there a universal synthetic principle that can be developed to create structures of whichever symmetry I want and however big I want with different kinds of, gaps or, that is created? You can clearly see that the metal organic frameworks have this cavity that unfolds, which I sort of did not tell you about the structure, is that just like skyscrapers, they are home to molecules, right? So now, what was the idea? So since it's metal and organic, we'll have to come piece by piece. Almost, in the 19th century, there was a very well understood idea that organic molecules do like metals. They do come into interaction with metals and create complexes, which were called organometallic complexes. Some of them are very famous, like the arsenic tetramethyl diarsine. But what really took place in the 20th century, in the early part of the 20th century, was there was a German chemist, Alfred Werner, who defined what a metal complexes should be, written at, how they should be written at. The metal can be defined to have an inner coordination sphere, which means there are ligands inside the sphere which are not accessible from outside unless there is an exchange that takes place with the ligand with the outside. And there are ligands outside that outside of the inner coordination sphere, which are sort of balancing out the charge. So this inner coordination complexes idea was very critical for the development of all coordination complexes from that point on, because the inner coordination sphere has a symmetry and directionality of ligands. You can clearly see it's not a spherical, it's not a sphere, it's an octahedron, right? So now the precise concept was, if I have these kinds of octahedral units, I have directionality of the ligands. Can I make use of this anisotropy from sphere to octahedron to actually stitch things together? And that was the precise idea by which the Nobel laureates came to fruition of the structures. However, it should be noted here that the entire Nobel Prize winning work was done in the late 80s and late 90s. What were inorganic chemists doing? It's quite strange, right? That you have some sort of an inquisitive behavior that chemists usually show. Can I stitch things? Can I stitch metal complexes together? Well, interestingly, there are rules for it. And this has been the hard part for chemists. The part that is kind of bothersome is in the carbon backbone, everything is a covalent bond. Those bond strengths are in the order of 400 to 600 kilojoule per mole. And that is a large energy to pay, right? 400 to 500 or 600 kilojoules is at least 20 to 30 times room temperature, okay? So when you have such, or maybe 300 times room temperature, when you have this kind of large, strong bonds, connections will have to be very rigorously done chemistry at high temperature. However, with the metal systems, the metal coordinate bond, the metal carbon or metal nitrogen or metal oxygen bonds are not as strong. They lie somewhere in between 100 to 400 kilojoule per mole. And because of that, and because metals are a blob of bigger charge than carbon, these are very flexible bonds. These bonds can come, the two atoms can come off, come on, come off, come on. Even if with 200 kilojoules per mole, you can have exchange between the ligand and the metal in microseconds to seconds. So these benzenes, you never hear carbons coming off, coming on, right? But with metal ligand complexes or metal atom complexes, these are pretty regular. You get lability in the bond. Now that makes it a slightly difficult proposition to polymerize, because the moment you go there, these things come and off, come and off. So you don't know whether you want you will have a stable structure. So that was one of the big challenges. But if you think about it, if you were to just have two parts anisotropically colored in the same complex, somehow there's a reactive end on two edges, you can start doing reactions and keep going across the reactive edges, right? You can bring things together and build up through the reactive edges to create a 1D chain. You can do that in 2D, you can do that in 3D. So in principle, there could be a code in which reactive ends are programmed in such a way that I can make a one-dimensional chain, a two-dimensional chain, or a three-dimensional chain on 3 different steps. Okay? So that was a possibility, and whether that could be done or not, that was the question. So the inherent part of that anisotropy comes from the metal center's symmetry. So the metal center can have tetrahedral symmetry, it can have a planar structure, it can have sort of this kind of a bipyramid on a triangle. You can have a square pyramid, you can have an octahedral, you can have all sorts of symmetry. And because of that, those are the parts from which you can build the structure in different angles with respect to each other, right? So the space is a spherical blob, but you can choose out of that few different angles in which you can build the structure, right? So it's a very nice space, mental exercise. How do you build things with that? One of the big successes happened in 1959, and this is not mentioned in the Nobel Prize Committee's lecture notes that you would go and read. This is by Yoshiko Saito. He was a Japanese inorganic chemist, and he sort of was one of the first inorganic chemists to solve stereochemistry at a metal site with X-ray crystallography. And he showed that you can use these kinds of very interesting ditopic, we call it, ligands. That means two reactive ends at the two edges. These are cyanides. You can use them to link these metal sites in like a diamond-like lattice. This was published in a very sort of not very relevant journal for the main group of chemists, but in a Japanese society journal, which is a pretty good journal for the society, the Chemical Society of Japan. But in 1959, this was as a crystal structure published, nothing was stated, why he made it, was it a reaction product that he just looked at. So later on, almost 30, 40 years apart, Siegfried Hunig, he's an organic chemist. He was looking at TCNQ, and this is the physicists would know this very well. TCNQ and copper complexes were known to have extremely high conductivity. In fact, this complex with copper and TCNQ showed almost 10 to the power 5 times conductivity of a regular copper strip, for example, at 3.5 Kelvin. That kind of told you that these arrangements, these specific polymeric arrangements are possible in systems and crystallizable. It told us that they are crystallizable and they can be made use of for many, very interesting reasons, okay? One of them is conductivity, of course. The sites are very nicely positioned in a lattice. But what has happened was Richard Robson, and this comes the first Nobel Prize, Nobel laureate, Richard Robson from University of Melbourne in the early 70s, had started his independent position, and he was looking for ways, as an inorganic chemist, looking for ways to bigger structures. While teaching a course for few students in the freshman chemistry, he was given wooden, sort of model builders, which was hard for him to show all the different kinds of structures he wanted to show the students. So what he told the students was that if you can use just sticks and imagine the balls as molecules themselves, wouldn't it be interesting to see how much symmetry can be used of a molecule to open up larger structures? And this is what Richard Robson sort of thought about. And when he got a chance, he replaced that cyanide. So you see this very flexible diatopic ligands with two cyanides. He replaced it with a rigid molecule with a tetrahedral symmetry inbuilt to it. It's a carbon with cyanides all positioned in a tetrahedral arrangement. Rigid tetrahedral arrangement, and he knew that the copper site is this one, and it was also known here that the copper site is always tetrahedral. Copper 1 prefers tetrahedral geometry while the ligands are going up. So he said, let's match the copper symmetry to the ligand symmetry, which is rightly rigid, and let's mix those two and do a solvothermal synthesis. And he could get these beautiful crystals, which he could solve, and he could show that indeed the two symmetries matched up pretty well to get a diamond-like structure. Again, not much different from this, but more packed, actually, more packed. But you have these nice pores that have emanated, and these pores would be in the order of few 1 nanometer or 1.5 nanometer. Now, he published these two papers in 2 consecutive years, and he stated without any question that you can create infinite polymeric frameworks consisting of these sort of metal complexes connected by rod-like segments. The linker was, he thought, is a rod, and the node are the metals. So this is the idea that he put in. What is interesting also is he laid down the groundwork and said, and I'm not going to read out too much from these paragraphs, but one of the important aspects was that we can have limitless range of these connecting units, right? We can change the symmetry of the connecting units. We can change the symmetry of the metal. So there could be limitless possibilities of connecting these together and creating polymers. Now, what was also kind of told that the bridging, the linkers, if you were to sort of change or functionalize the bridging ligands, you could also probably tailor the structure. So while reading these papers, Sushumi Kitagawa in Kinki University, and this is, he was moving to Kyoto from that point on, but in a very small university, he looked at these copper 1 chains again with different kinds of connecting ligands. Now you look, these connecting ligands are slightly different. It's much smaller, okay? And they have a different kind of symmetry. They're planar molecules. They're not tetrahedral. So this kind of sort of mixing of the copper 1 with the ligands opened up a planar geometry, two-dimensional material. And that two-dimensional material had a symmetry, almost looking like a cyclohexane shape of copper systems, right? Then he could change this ligand and make it more sterically hindered. And now these loops would not close. Now they will open up and make a one-dimensional chain of copper, these polymers. So it clearly told us that this linking unit has an enormous influence in what the symmetry is expected. And this could be predictable. That was the idea. It is predictable. So he then showed almost 5 years down the line when he moved to Tokyo Metropolitan University, and I saw that there was a similarity with the Japanese Nobel laureate in your case. They probably were at the same time. In Tokyo Metropolitan University, Kitagawa actually demonstrated the first use of porosity from these frameworks. And what he did was he used a pentagonal bipyramid structure of a cobalt now. He left copper out of the window and he went to cobalt, and cobalt demonstrated that these are 7-coordinate cobalts that can be used now to build structures which were interdigitated, as well as they had symmetries so that they can open up channels while they are digitated, open up channels along a direction where you have a larger pore, larger access to, you can keep molecules inside. So he showed that you can put in gas molecules, small gas molecules like methane, dinitrogen, oxygen, and you can do adsorption, desorption kind of isotherms. You can create isotherms of adsorption, desorption. Yes, I'll be there. So when these things happened, the excitement was all about that, yes, these materials are possible to make with the right choice of the metal site and the ligand, and you can tune the symmetry of the entire structure by tuning the symmetry of the ligand and the metal. However, the problem was all these metal polymer, coordination polymers would break apart. Once you sort of try to push in the gas molecule or take the gas molecule, they won't work as regularly, systematically, in some sense, reproducibly every time. And that was the issue that Omar Yagi came and solved. He looked at that you have these original metal organic frameworks had a charged motif. Okay, they always have some sort of a nitrate, or in the case of Robson, it was a BF4 minus, which was stuck in the cavity. So the question that Omar asked, can we use anionic counteranions already as ligands or the linkers? So when he looked at that, he asked the question that, oh, can we use carboxylic acids? Because these can be deprotonated and they will be charged now. Unlike pyridines, they are charged. So they will compensate the metal's charge and they will not leave any counteranion along in the pore. So once that was done, he could show that pyridines can be put as guests inside these structures and you can have cyclic structures. Again, one problem solved, the structures remain stable. You can push pyridine in and pyridine out, but still, when you remove the pyridine or anything from the cavity, these would still collapse. So this was, of course, the first report of these 2D sheets, which were very stable. But this was the brilliance of Omar Yagi that changed the field and produced MOF as we know it today. What was the critical idea? So the metal node that was used by everybody in the community was a single metal site. And when the single metal site, why did it fall apart? Because they're always continuously exchanging ligands at any part of the node. Okay, so there'll be defects created all the time. What Omar Yagi said, I don't need a single metal. I can make a composite of metal, like a metal cluster, with the same symmetry. And if I can do that in organic part, I am done. I will have a composite metallic node, which will be much more stable than a single metal site. And once that was shown, Omar Yagi demonstrated the first gas adsorption, desorption experiments reproducibly, or going back and forth for 100 times without change of structure, without loss of structure, and could keep the metal organic framework stable. This was published in 1998. And then this is the Roger Federer structure, which is essentially you can create all of these sort of large structures with different classes of these metal nodes and a slightly larger kind of a ligand, which is a bicarboxylic acid. Instead of a 3-carboxylic acid, he used a ditopic bicarboxylic acid, and he could create one of the most elegant structures that we could make. And these structures had 2 nanometer spheres that could be put inside. That is the cavity size. And the amount of surface area that you can generate is 2,900 meters square per gram. That's a huge amount. It's like a football stadium if you were to consider atoms as human beings. So this is a huge amount of surface area per gram. They beat all the record that existed till that time of activated carbon, which was 1500 meters square per gram. So this told us there is enough open sites in the material. In fact, 60% of the volume was open. The rest of it was this grid, the wireframe. So Kitagawa revisited his thoughts and he demonstrated that yes, Omar Yagi has this, but then one should think about very, very dynamic structures so that those are not just rigid, but with guest encapsulation can change shape because the applications would increase in that case. So Kitagawa predicted dynamic frameworks, and Omar Yagi and O'Keefe, whose ideas in solid state chemistry were already there, they said, I can make any tessellated structure by just changing the metal node and the linker. And all of these are structures that they made. This is all reviewed in a paper in 2024, but these are tessellations done with the metal and the ligand, and you can have Escher-like diagrams for these kind of projected on 2D. What was interesting is they renamed this field as reticular chemistry, where you just use symmetry principles in solid state and define your structure before making the structure. And you can clearly see that the sizes of ligands can be varied, the classes of metal clusters with the symmetry can be varied, and what you get is a range of network structures. And all of these are now being made possible to be built because of the work that Omar Yagi with O'Keefe did. These are all, these can be interdigitated, these can be of different kinds of symmetry, you can clearly see. And what else you could do is you can increase the size of the void space so that that 60% volume can be gone on to increase to 90%. So everything is possible with this kind of reticular chemistry. In fact, because of that, since 2000, there is an upsurge of structures being reported. In fact, so BASF, a German company, collaborated with Yagi to produce the first CO2 capture MOF in gram quantities. Like you can buy it, in 100 grams and kilos. Yes, just to end, all of these beautiful structures have a purpose. They're not just sculptures. They can actually store hydrogen, CO2 to a huge amount, more than any material that is known. You can actually incorporate proteins in them. And these pores could be up to 10 nanometers. In fact, not just that, what you can do with these is you can harvest water from desert. If you have the right kind of the metal organic framework, water can be bound inside the framework in the hydrophobic cavities of the framework, and you can generate 250 grams of water per kilogram of the metal organic framework, even at a 7% humidity rate. So we can discuss this later, but Omar Yagi clearly demonstrated that. Just a quick piece of sort of nugget about these three people. Except for Yagi, these two are pretty gentle scientists. The idea that Robson came up with this beautiful structures and talked about this in the freshman courses really started and triggered the field. Kitagawa's idea of using the space, thinking about the space and modifying the space by interdigitation was his brilliant contribution, and of course Yagi did all the rest. Of course, all their legacies also live by students who are colleagues of us in India, Rahul, Tapas, and Sujit. They're all extending the reticular chemistry in different directions, covalent organic frameworks for catalysis and for decontamination of water. All of these arsenic ions could be trapped in. And I would like to end and just say that there is a lot more space to explore with these structures, hollow structures, as Manoj called. And it's always great to think about chemistry in confinement. This is something that we also engage in quite a bit. And I want to thank Manoj for letting me do this, because I went through this literature that was amazing to see, and see chemistry with all its power being done with the right design principles. Thank you.
Thank you, Jyotishman. I think we'll have questions from, so we'll throw open for questions. You can ask any of them. So if you can come over.
So in 1987, Michael Crichton wrote a novel called Sphere, in which they find this spaceship at the bottom of the ocean, and they find out it's a human spaceship sent from the future, and it's sci-fi.
Right.
Same author who wrote Jurassic Park. In that, they find that the surface of the spaceship is made of a metal, organic composite polymer.
Okay.
Yeah, that's the words used. I mean, there
Okay.
is no further chemistry explained. That was in 87, and if it has to be the
Those who are leaving, please go. Feel free to go and have tea and snacks.
if it's the surface of a spaceship, it also has to be like a ceramic, like highly thermally resistant and so
Right.
on. And I saw that in your slide, this prediction was dated to 1990 to the scientist.
Right.
So, I mean, I went and verified the actual date. So,
Right.
Michael Crichton made the prediction.
Made a prediction. Yes, absolutely. No, that's a possibility. It's just a
Vague collection
yes.
of words.
However, what I wanted to say is, the metal organic frameworks were not coined till 1995. So whatever happened in 1990s was early parts of 90s was just polymers. We used to call it as coordination polymers. Didn't have this porosity of an idea that generated.
This was like a prediction about what human future
Sure,
sci-fi would
sure,
do.
sure.
So I had a question, like you said that the key turning point was changing a single metal site
Yes.
to a cluster
Yes,
with the same symmetry that can take
absolutely.
so long.
Yes.
But
yes.
what about the same drawbacks about the increased lability that you mentioned with a single site?
So,
Won't that be carry forwarded even in a cluster?
no, it doesn't, simply because what happens in the cluster, the ligands are actually, there are multiple ligands holding the same metal, and that affects the lability of the outside ligands being bound to the cluster. Okay? If a single metal is there, it's only the inner coordination sphere is exchangeable in the regular MOFs, right? But if it is a composite, now you have other ligands to balance out the interactions, and hence the lability is compromised. Yeah, that's a very critical idea. Yeah.
Okay, JD, for you,
Yes.
what about O'Keefe? I mean, he's
Yes.
done a lot on this.
So,
And you said you'd tell us about the two Johns, but you never did.
yeah, O'Keefe was the guy who challenged Omar by showing the zeolitic chemistry and saying silicon is being used for all these porous structures. In fact, Vivek in our department makes these silicon nanostructures, right? That has been known for a long time. What O'Keefe said is, can you use those symmetries in silicon and use any metal in the periodic table and do this for the MOFs? And that's what Omar Yagi showed. Omar Yagi worked with O'Keefe to define reticular chemistry. So O'Keefe has a huge contribution. He has won prizes with Omar. The other ones, not this one. Vijay?
Yeah, so the other Johns. So after my PhD at Yale, I went to Berkeley for my postdoc. And my very first project was with actually a student who was being shared between my postdoc advisor and John Clark. So I worked closely with him and his student, and we published several papers. John Clark, by that time, was already a very senior professor, close to retirement, but very active. Used to come to all the colloquiums and was very British as well. John Martinez, even in some of the Nobel-related articles, he was the engineer. I'm sure if you know this, but if not, these three were a advisor, postdoc, grad student pair when they did this experiment at Berkeley. So John Clark was the PhD advisor. Michel Devereux had done his PhD in Paris and then was a postdoc there. And the early experiments into these looking at quantum effects in electronic circuits was already happening in France, in Paris, in Saclay, and other places. And John Clark was working on using these Josephson junction-based squids for magnetic sensing and looking at some of the more fundamental properties. And John Martinez was described as the engineer in the group. So he had the engineering bent of mind to figure out how to get this experiment to work in terms of controlling the noise, probably what the design is. I don't know the exact details, but I have interacted with John Martinez actually from a very early days. He visited Yale, I think when I was still in my first or second year. I remember telling him about the experiment I was planning. And later on, actually, the Yale group, which was Michel Deveray and another younger scientist, Rob Sholkoff, and John Martinez, they became arch rivals. On the every March meeting, they would, there'll be like constant back and forth and digs being taken at each other. But I have to say that John Martinez was probably the first person who really wanted to build a quantum computer. In the sense that in the early days, around the time I was starting my PhD, the whole idea of quantum bits, doing 1 or 2 qubits had picked up. And of course, there was a lot of promise and hype as well. But a lot of the scientists were still interested in doing that for just understanding the physics. But John was absolutely adamant that he wants to build. He still says that he wants to see this machine in his lifetime. And for that, he has changed some tracks on how he's approaching it. And this was also the reason why he stuck to that original design, which is actually this experiment. The size of the Jyotishman junction was much bigger. The kind of devices, for example, we make in our lab, and which is the most popular design, the Jyotishman junction is about 200 by 200 nanometers. And that can only be done with electron beam lithography. Whereas a larger Jyotishman junction can be done with optical lithography, which is closer to how semiconductor chips are fabricated. And he said that there is no way we can make a quantum computer with millions of qubits using electron beam lithography. It has to be optical. So he stuck to that. But unfortunately, because of some physics of large Jyotishman junctions, they were just too noisy. He tried very hard. He actually reached a lot of the early milestones in quantum computing demonstrations with very bad qubits. But just because he could get them to engineer really, really well, and he could do things in a very short amount of time, but then it just could not get better. And then he also shifted to the conventional design. And now he's going the other way to say that, look, I'm going to bring in principles of semiconductor fab and adapt that to superconducting qubits and not do the other way around, because we already know how to make billions of transistors. So let's start there. But one has to see what happens. But yeah, I mean, John was like a brilliant engineer and scientist, and had great conversations with him as well. I have one paper with him because we collaborated on one particular topic where they were getting into it newly, and that was like my entire PhD and postdoc work. So we worked together.
Yeah.
That's great.
Is it important for the complex metal organic complex to be symmetrical? Because I'm thinking, because ATP, it forms a bond with magnesium. So does it qualify as a metal organic complex, or can we make a lattice of it?
So you need to have extended structures, and that unit being repeated on top of each other for distance of microns to millimeter. Only then I can call it as a framework which is extended, and it should be crystalline. I should be able to crystallize it. So if that is satisfied, then that's not you can call things which are frameworks.
And
it will be called a polymeric frameworks, but anyway, yeah.
Question for Sulabha, ma'am. So FOXP3, is it only present in CD4 and CD8 positive cells, or is it present in FOXP3? Is it present only in CD4? Not in B cells or other T cells?
If you're not rationing questions, I have one for each of these. Yeah, go ahead. So Vijay, you said the transition as you increase the current, it goes to the normal state. You could explain why that happens to the general audience?
So this system, see, if you have just a superconducting wire, it also has a limit for how much current you can pass. But that is a different piece of physics, which ultimately, your superconductivity breaks down and then you get normal. Here, we are actually talking about much lower currents. That magnitude of that current is dependent on the overlap, like how large the junction is and how thin or thick the barrier is. So the thinner the barrier, the larger the critical current, the thicker the barrier. But usually that goes exponentially with the thickness. So for most devices, the thickness is more or less fixed, and you just play around with the IR. So essentially, as you start applying this current, the phase across the two superconductors, they get twisted so much that after that, it basically becomes unstable. And then it no longer supports. And that, so this, if you remember, the Josephson relation said that if the phase is constant, then there is no voltage. So in the mechanical analog, it's the situation where the pendulum is getting tilted and tilted and tilted and tilted and tilted and tilted, and this is like the critical current, and then it goes boom, 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 like keeps going round and round and round. So that is the two different states. So it behaves like a normal tunnel junction, as if the two sides were a metal. So this is what he had predicted.
Well, about this thing about T cells for cancer, you said that. So therapies are based on now.
So the other way around, therapies are based in trying to
Reduce the.
Increase T regulator activity.
Yeah.
So that the cancer tumors escape in the liver.
Correct. So if you want, people are suggesting tests for cancer. So they suggest various things. Do a blood test and you can figure out whether this guy is likely to get cancer or not. So any of these things monitor at this level?
Other charts, what is
Okay.
prognosis?
Okay.
You look at helix and we have high prognosis.
Bad. So it's a marker for. Question there?
Question to JD about the periodicity in this metal organic frameworks. So if you look at inorganic crystals, like the symmetry and what it will crystallize is like heavily dependent on what is the size of the atoms and how they are interacting with all the atoms around.
Right.
In this metal organic frameworks, essentially the unit cell you would see, the unit of periodicity, it's very large. So how essentially, I mean, we are able to manage that they would be periodic and they would be.
So all of these are solvothermal synthesis that's done so that you attain the lowest ground state for the system as you heat up and you let them cool and you crystallize out of solution. Now, the way this is working at the molecular level is that one metal unit, whether it is a composite metal cluster, how fast is it exchanging ligands with the original ligands that existed in the metal cluster with the ligands that you have provided as the connector or linkers, right? And if you can build it, since these are still dynamic, as you build the structures, there will be defects that will appear, but because you're doing very high temperature growth of these systems, it will self-sort to remove all the defects, and get trapped at a thermodynamic product at the end. And that thermodynamic product is the repeated unit which opens up. These things are not very big. The pores are in the order of a nanometer in regular units, a nanometer to 2 nanometers. These are not really large. But what stabilizes them is that one critical cyclization of these systems, right? And that is true for even for the all organic. So I didn't talk about, but some people are developing, removing the metals, all organic carbon frameworks. Is the same idea that you need to make these cyclic structures to grow. So once those cyclic structures form, then you can sort of think of the two dimensions.
Hello. Yes. My question is on that there is a graph, right? Like temperature versus this thing. You told due to the tunneling effect, it saturates. So you told the problem is solved with using the magnet. And so can we also use like different thickness? With thickness, the quantum tunneling will vary. So the saturation level will be different.
Yeah. So, so the problem, it was not that the saturation problem was solved. The saturation was actually the signal, which was to show you that this is quantum tunneling. But you can raise an objection and say, well, it is getting saturated because you have extra noise in your system, right? So the temperature keeps coming down. So the noise related to the temperature is constantly coming. But if you had some constant noise in your system due to some, technical issues, then the escape will still saturate, right? It could be a coincidence that it's saturated exactly at that point. So in order to prove that, they changed the critical current by applying a magnetic field and showed that no, when I lower that transition temperature, my system is still cooling down to those low temperatures. Now, the question you asked, yes, this experiment can be done by two different devices. with different thicknesses or the area of the junction to go from the quantum junction to the classical junction. But then that would have been two different experiments. There's no way to know that everything was identical in those two experiments. So the in situ control was critical, that they could do it in exactly the same setup and only one parameter was varied, which is exactly what they wanted to change. So that was the reason it was done like that.
Okay, so last.
Yes, so when we are at the high temperature, a few hundred millikelvin, you can even think of this as the effective Johnson noise of that resistor, which is representing the environment, which is causing the system. So there is a DC current, and you can imagine you can basically construct an equivalent voltage noise source or a current noise source, and that is basically causing the system to jiggle around. So if the experiment is done correctly, it should only be the temperature. And that's the very, very hard part. I mean, I have done this experiment myself. It was a nightmare to do this and get it correct. And that was, I think, a big achievement. And they basically invented various tools, which I did not have time to go in terms of the kind of filtering, the packaging, the choice of the parameters, which are now all best practices, which are used in all of these experiments, even today.
Can we measure the vacuum fluctuation at the Jyotishman junction with the Cooper pairs? Whether the effect of vacuum fluctuations will be there in the Cooper pairs?
Yes. So these are often matters of interpretation. You can think of the tunneling as due to vacuum fluctuations. The reason I did this experiment again during my PhD was because I was trying to look for a similar effect in a different system where it was predicted that tunneling will not happen. Because of it being a driven system, the vacuum fluctuations actually convert into real fluctuations, and the saturation happens at a different temperature. So the last chapter of my thesis was exactly this, to show that this happens. And I had to do this experiment just for the same reason, to show that my system is actually cooling down to those temperatures, and the saturation is not due to excess noise. So in my experiment, the tunneling was predicted to not happen because of other reasons of the physics of the system. So yes, you can see the effect of quantum fluctuations in various ways. This is routinely done in all these experiments these days.
Close down the session now. So thank all the speakers again. Thank you very much for this exciting session. So please join us for tea and coffee and snacks.